Welcome, everybody, to this week's installment of the UAA Professional Development Seminar. I am your host, Dr. Scott Hamill, and I am the chair of the Civil Engineering Department here at UAA in the College of Engineering. Those of you that have been attending regularly this semester will recognize me, since this is the third of 4 civil engineering themed seminars for the semester. And today it is my distinct pleasure to introduce you to today's speaker, one Ellen Hamill. You may notice a common last name there. Ellen has 15 years of experience in structural engineering. She has a bachelor's degree from Tufts University in Boston and a master's from the University of Colorado in Boulder, and has been in Alaska since 2011, and has done lots of design of lots of different things, including buildings and docks, pedestrian and vehicle bridges, which is quite rare for someone to do both buildings and bridges. So with that, her topic today is the Gruening Middle School Earthquake Recovery Project, for which I know there is lots of interest in the community. So with that, I will turn it over to you, Ellen. And yep.
Thank you, Scott. As you mentioned, I'm going to be talking about the Gruening Middle School Earthquake Recovery Project, and we just reached completion on that last week or 2 weeks ago. I was at the ribbon cutting ceremony, so it was a very proud, momentous moment for me and the other people who have worked on the project. Again, my name is Ellen Hamill, and I am a senior engineer at Reid Middleton here in Anchorage. As we stare at this cover shot, I just want to take a minute to point out the state of greening in this photo here. What we're seeing is the wood shear walls on the exterior of the building. And prior to this project, the exterior of the building had a 4-inch brick veneer on it, which on the one hand was durable, but it also added a lot of unnecessary seismic weight. So one of the grand things about this project is that we removed all the brick veneer on the exterior of the building. So this is kind of an intermediate picture where the brick veneer has been removed, but the new siding has not been placed. And we'll talk about that in a little bit later. The main things that I'm going to discuss today are the design history, which is interesting. There's the original design and then the corrective actions, as well as a couple of structural renovations that have happened in the past 10 years. In 2018, there was significant damage to Gruening Middle School. The most prominent was the detachment of a 2-story CMU wall to the roof framing and the roof diaphragm above. There was also CMU spalling, especially at CMU corner intersections and column embeds. In addition, there was bending of a gym curtain wall support beam and damage to a stairway wall to column connection. The Earthquake Recovery Project with the school district is broken up into 3 different parts, and that's primarily due to funding. The first component of the project was earthquake damage repairs. The second was seismic improvements and roof replacement. And then the third encompasses safety, security, efficiency, and environmental improvements. It's an efficient opportunity to take care of these items while we're doing other structural items. The original design was done in 1981, and on the right of the slide is a plan view of the building, and it's essentially an X shape. And then the big open space on the left is the multi-purpose room, or the MPR, and the open space on the right is the gymnasium. On the top there on the north is the admin spaces. There are 2 levels to the building with multiple long ramps that run the length of the hallways. The gravity system is wood joist, and the lateral system I found to be very interesting. It's a combination of wood shear walls on the exterior And those wood shear walls are the ones I discussed earlier with 4-inch brick veneer. And then on the interior of the building, the lateral system is CMU shear walls. One of the most fascinating parts of this building to me is that if you were to look at a wood shear wall with brick veneer, and then if you were to look at a CMU wall, they look exactly the same. The only way to for sure know the difference is to do destructive demolition to find out. So you can't just tell by looking at them. In 1984, the as-built were completed. So between 1981 and 1984, this is primarily anecdotally, it was discovered that the original design used a seismic load factor that was about 3 and 7 times too low. And the implication of that was that the entire lateral system needed to be upgraded. So a very large overhaul of what we call corrective actions was done. And these corrective actions included added shear walls and upgraded lateral connections. To give an idea of the scope or the breadth of these connections upgrades, there were 204 pages of upgraded details in the corrective action set. So a very significant, a very sizable effort was done to upgrade Gruening Middle School as part of the corrective actions effort. So that's why there's a length of time between 1981 and 1984. The as-built were dated in 1984, whereas the original design was done in 1981. Within the past 10 years, there's been a couple renovations, fairly minor, to Gruening Middle School. In 2013, the CTE or Career Technical Education area was upgraded, and this included infill of CMU walls, new windows, and new hold downs. In 2017, the special education area was upgraded, and that involved new shear walls, new ceiling tiles, and new shelving. In the plan view on the right, the shaded area is the special education area. One thing that's interesting to note is that the special education area performed very well during the earthquake, so well that there was no damage, and the contractor decided to set up shop there for construction offices for this recent project. Also interesting about the special education area, in addition to the structural upgrades that and I say we because Reid Middleton was a part of this project, in addition to the structural upgrades, there were architectural upgrades, or what we call non-structural upgrades, that performed very well during the earthquake, such as wider ceiling edges on the ceiling tiles, and also shelving that was slightly sloped backwards so that items did not fall off shelves during the earthquake. So these minor upgrades in terms of non-structural upgrades had a significant impact on how this area behaved during the 2018 earthquake. The 2018 earthquake was a 7.1 magnitude earthquake, and it occurred on November 30th, 2018. This image here shows the epicenter with a little cross, and then the red dot is Eagle River, which is the location of Gruening Middle School. It is Eagle River and Gruening Middle School are located northeast of Anchorage and almost directly east of the epicenter of the 2018 earthquake. Following the 2018 earthquake, Reid Middleton was contracted to visit every single one of the ASD facilities, and that includes 91 facilities, schools, and other buildings that are part of the school district. We use the ATC, or Applied Technology Council process, to review every building, to walk through every building. And following our site visits, we placarded each building with either a red, yellow, or green 8.5 by 11 sheet of paper. This picture here is an example of one of the red sheets. So red means stop, red means unsafe. And and Gruening Middle School was marked red due to the significant structural damages at the location. Within 1 week of the earthquake, 89 facilities within the district were reopened. Gruening Middle School, we had 3 site visits by Reid Middleton within 2 weeks of the earthquake, and the middle school was tagged as red. A side note here, the building was tagged as red due to the detachment of the 2-story CMU wall. However, there were some initial concerns that there was perhaps a lens or a void beneath the school. There were initial concerns that there was sloping in the gym area. And to address these concerns, there was a geotechnical engineer that got involved, and we had some drilling done, as well as a land survey came in to see if there were significant issues with the geotech in this area. Based on the land survey information and the borings, it was determined that the soil beneath Gruening Middle School was adequate. And what this told us was that it would be appropriate to repair Gruening rather than rebuild at a different location. And this image here shows the 2-story CMU wall that I've referenced a couple times. The brown diagonal pieces are the temporary shoring that the contractor put in place to provide a safe environment for the contractor and other professionals visiting the area. This is at the south wall of the gym, this figure, but similar 2-story walls exist at both the gym and the NPR. And again, this detachment is why the building was tagged as red following the earthquake. Another significant area of damage following the earthquake was CMUs falling throughout. It was a particular concern at corners and column embeds. And in addition, there was falling of the 4-inch veneer and the 4-inch veneer on the exterior of the building. The first 2 pictures here show a condition where there was an interior CMU wall attached to an HSS steel column. And you could literally stick your hand in between the CMU wall and the column. So this was a significant damage and something that we remedied during the earthquake recovery project. The figure on the right shows the brick veneer on the exterior of the building and pieces of veneer that have spalled or cracked following the earthquake. Another item that was damaged during the earthquake was the gym curtain wall support beam. There's the curtain hanger there in silver, and that obviously is damaged, but the black I-beam was bent such that that curtain no longer functioned properly following the earthquake. As part of our renovations in this area, we actually demolished a significant portion of the curtain wall and then added lateral support for the remaining curtain wall beam. An additional item that was damaged during the earthquake was the wall attachment, the stairway wall attachment to a concrete column. And the picture here shows the temporary solution, which was just a bent plate anchored to both the concrete wall, or pardon me, to the concrete column and the adjacent wall. So looking at the earthquake recovery project, again, it was a 3-fold project due to funding sources. The first portion we labeled as FR, or FEMA repair for short, and that was all the earthquake repair items. So the top of CMU wall, the stair connection, the gym curtain wall support beam, all those items were noted on our drawings and the associated architectural, mechanical, electrical drawings. Any sort of earthquake repair item is tagged as FR. Earthquake mitigation and re-roof efforts were tagged as FM, or FEMA mitigation. And again, this was an effort not only on the structural side, but all the other professionals involved in this project as well. items that were not labeled as FR or FM were simply left without a tag, and that would cover any sort of security upgrades, or there was some reconfiguration of classrooms. So those did not have a note such as FR or FM. The design process we used as structural engineers was twofold. We used ASCE 4113, seismic evaluation and retrofit of existing buildings for existing structural elements and retrofit. Any new items such as the front and back canopies, which I'll show pictures of later, were designed per ASCE 710. ASCE 710 is minimum design loads for building and other structures. So the first group of items I'm going to discuss here are the earthquake repair items. In this picture on the right, this is one of the orchestra classrooms, which had a tall CMU wall with inadequate attachment to the roof. In this picture, you can see a steel plate that's anchored to the wall. And this happens on both sides of the wall and prevents lateral out of plane movement or detachment of the CMU wall. The solution that we provided was either a plate on either side, which would prevent movement in both out of plate directions, or another solution that we provided was to have a plate on one single side of the wall and then put a through bolt in the wall, and that provided out of plane that provided a restraint for out of plane bending in both directions. This was a significant effort on the project. The top of CMU wall attachment was over 700 linear feet. That means that this detail was provided along 700 linear feet at Gruening Middle School. So one of my favorite comparison pictures, the picture on the left, shows the top of CMU wall that had temporary bracing, and that was prior to the Earthquake Recovery Project. And then this picture on the right is an October 2021 project, or 2021 picture, and it shows the new detail at the top of the CMU wall to provide adequate restraint. And also in this picture, you can see that the CMU wall is fenestrated or scalloped on the left, and then the CMU wall on the right is not. And the reason for that is because there is an FRCM overlay, which provided enhanced earthquake performance. We'll go into detail on the FRCM a little bit later. The earthquake damage repair also included upgrades of the CMU corners and column in-bed connections. Corner reinforcement was added, and then at CMU wall intersections. And then if there was a steel beam, then there was a piece of rebar added to connect the CMU wall to the steel beam. What the contractor elected to do to add this additional reinforcement was to remove the face shells of the CMU, put in the reinforcement, and then reattach the CMU face shells. The gym curtain wall support beam was upgraded as part of our project, and as discussed earlier, we ended up removing about 50 feet of this beam because the space was reconfigured. In addition, we added lateral support in the longitudinal direction. The existing curtain wall support beam had lateral support, but only in the transverse direction, not in the longitudinal direction. So as part of the project, we added lateral support in the longitudinal direction. This is another one of my favorite pictures because it shows the removal of the CMU on the exterior of the building. And I put this kind of early in my discussion here because it had significant impact to the rest of our calculations. The removal of the 4-inch block veneer significantly reduced the seismic weight of the building. The brick veneer was approximately 50 PSF in weight, whereas the new lightweight siding was less than 10 PSF. So not only is there a new look to the building, but there are significant structural implications to removing that amount of weight. As part of our repair project, we reinforced the attachment of stair stringers to the adjacent wall. So what this did was positively attach the stair stringers to the adjacent wall so that there wouldn't be a detachment of the wall to the column connection. And we did this using tension ties attached to the stringer, from the stringer to the wood stud. In addition to the earthquake repairs, there was also significant earthquake mitigation efforts as part of our project. One of the most sizable efforts was to evaluate the existing wood shear walls and upgrade them as necessary. To do this, we added sheathing in many locations to achieve double-sided shear walls. And also some walls that weren't shear walls, we turned into shear walls and added a few new walls on the project. We also added hold downs and again added some new shear walls, some of which were single-sided and some of which were double-sided. These images here are from the structural drawings on the recovery project, and it shows a plan view of a new or a plan view of an upgraded shear wall as well as our shear wall schedule. This particular wall was upgraded to an SWSA, and based on the table, that means that the existing sheathing was a 1/2 inch single-sided. And then what we did was add sheathing on the
Might have lost her.
Can you hear me?
Yeah, now
Yeah, we can hear you now.
you're back. I think you lost your internet or something.
Could be.
Can you share your screen again? My camera's cutting out, so.
It's on.
Okay, can you hear me?
Yep.
Okay, let me share my screen again.
I think it changed microphones maybe because it sounds like you're in a big empty room, but that's okay.
Let me try again. How about that?
That's better.
Okay, let me try the video one more time.
Worst case scenario, you can leave the video off.
We just need like the screen share. If audio works, it should be fine. But if audio
Yeah.
and video works, audio and video doesn't work, just audio.
Okay, you guys should be able to hear me now.
Yeah, that's the far away mic.
Okay, I'll try and speak louder. I apologize. I'm having issues with my initial mic.
Okay.
Okay, I will put back on the screen share. Okay, I should be up and moving again. You guys can hear me?
Yep. You
Yes,
just
we can hear you.
quiet.
Okay, I apologize. I'll try and speak louder. This image here shows the wood shear wall upgrade, and this wall in particular was upgraded to an SWSA. And as an example of our notation, SWSA means that the wall went from a 1/2 inch single-sided to a double-sided wall, both of which were a 1/2 inch. And then the number 8s, which have the triangle, are the hold downs. This image here shows the diaphragm corner reinforcement. And what this is addressing is there are many openings in the 2nd story of Gruening Middle School. It has a very open layout. So if you're walking on the 2nd story, there are many openings in which to look down, but there was no addressing of these corners, no reinforcement to prevent tearaway of the 2 intersecting walls or structural elements. So we added horizontal hold downs throughout the 2nd story to address the diaphragm corner elements. In addition to the diaphragm corner elements, we also added diaphragm strengthening. This was on both the floor, the 2nd floor level, as well as the roof level. For the floor level, what we did was add new blocking, and that was diaphragm strengthening from below. On the roof level, we added a new layer of plywood, essentially overlaying the existing diaphragm. And this was diaphragm strengthening from above, and it was something that was very simple to do concurrently with the re-roof effort. The existing CMU walls we investigated, and they were not sufficient to meet modern code requirements. The current code has minimum spacing requirements for both horizontal and vertical rebar, neither of which was met with the existing CMU walls. And then these walls did not have rebar hooked at the ends. The upgraded CMU walls were strengthened using fabric reinforced cementitious matrix, also known as FRCM. FRCM works in conjunction with existing CMU, and in this case added approximately 1/2 inch of thickness to the existing CMU. It was a sizable effort on this project and added approximately was applied over approximately 24,000 square feet of the building. We applied FRCM primarily on one side of the CMU walls, but in some locations we needed to apply the FRCM on both sides of the existing walls. This was because the FRCM was needed for out of plane loading demands. For the shorter walls, the existing CMU was adequate, had adequate strength to address the out of plane bending. I'd like to thank Simpson Strong Tie, and a particular thank you to Anchorage. FRCM was a deferred submittal. So as an engineering firm or as an engineer of record, I did not design the FRCM. We had a basis of design in our project, but the FRCM itself is a deferred submittal. So Simpson did the design calculations for FRCM, and then also helped with the install and educating laborers to be able to install the FRCM. On the left of the sheet here is our detail in our drawings, which shows how the FRCM is applied. The scallops or fenestration are shown in that image. And the first thing that's done is that sprayable mortar is applied to fill in those scallops. And then the bidirectional fabric or the carbon fiber grid is placed. And then finally, another layer of sprayable mortar. So it's a stepped process to apply the FRCM, the final product of which is a finished wall. And that's what the image there on the right shows. You have your existing wall, sprayable mortar, fabric reinforcing, more sprayable mortar to cover up the fabric reinforcing, and then the finished wall. This is an image of Simpson's shop drawings, which shows the grid or the bidirectional fabric. And then along the bottom of the wall, as well as on the side of the wall, those are proprietary anchors that are used to anchor the FRCM to the intersecting walls and to the floor below. The picture on the left here is are the contractors or the subcontractor installing the FRCM. We were very pleasantly surprised at how quick this process went. It was a new process for Reid Middleton to be involved in, and it went quicker than we expected and also quicker than Simpson and the contractor expected, which is always a great thing. On the right, those are images of the anchors. At the floor level, what's done is a hole is drilled, and then the anchor, which looks like a rod, is placed into the hole. And then the ends of the anchor are splayed, and those are attached to the FRCM wall. This happens both on the floor level and then along the sides of the wall. So this image here, or these images, on the left, you have the spalling. And you can also see the fenestration, the existing scalloping in the wall. And then on the right-hand side is what the finished product looks like. If you look very carefully, you can see the anchors there at the end of the wall, but in general, it's a very smooth finish, and it can be painted. Another thing that we addressed in our project was the catwalk bracing. This is in the MPR. We talked to some of the people, some of the users of this space, and they noticed that even during normal use, regardless of an earthquake, they told us that the catwalk was very jiggly, very wobbly to walk on. We took a closer look at the catwalk and also the existing drawings and noticed that the catwalk had no lateral support. So as part of this project, we put in lateral support by using 1/4 inch diameter rods in the horizontal plane. Another effort that we did for the Earthquake Recovery Project was to put in new roof framing to accommodate snowdrift. Per the Muni, anytime you increase your R value or your insulation value on a roof, you need to either show that snowdrift has been addressed before, or you need to address snowdrift. And what that involves is calculating what that drift or unbalanced snow load looks like, and then evaluating your existing framing system to see if it can see if it's adequate to account for the snowdrift or the unbalanced snow load. And what we found is that greening was not adequate that greening did not have adequate capacity for the snowdrift. So as part of this project, we upgraded the gravity system at the roof level to address snowdrift. This last part of my presentation is going to discuss the additional upgrades which didn't fall under FRCM, meaning they weren't part of a repair project and they weren't part of a mitigation project. This picture here shows the new front canopy, and it provides a very focal entry for Gruening Middle School. At this entrance, new security measures are put in place. When you walk in, there's a new admin space directly on the right-hand side of the building, and it goes in line with ASCE's preferred security protocols. On the back side of the building is a new, what we call a bus canopy. One significant civil effort on this project was to relay out the parking at Gruening Middle School. The parking was very convoluted, very messy, very frustrating and unsafe prior to this project. Now there is a new bus drive-through area in the back of the school, and it provides for a smoother drop-off and pickup situation for the children. So as part of that new layout of the bus and other parking, we put in a back canopy in the back of the building. Here's some plan drawings and a section of the front canopy. It has a significant LVL overlay and only one column outside of the building. As part of the earthquake recovery project, new mechanical units were put in the cupolas. So the cupolas are two pop-ups on the roof, one above the MPR and one above the gym. These existing mechanical spaces needed to be enlarged to account for larger equipment. So to do this, we heightened the cupolas, and we also provided a larger footprint for these cupolas. In addition to providing a new larger mechanical space, these cupolas also provide access to the roof from the cupolas, which was not available beforehand. Here's a section cut of the cupolas. There's louvers and also, like I mentioned earlier, people doors so that one could enter and exit the cupolas from the roof. In addition to enlarged cupola spaces due to mechanical upgrades, we needed to provide a couple of new mechanical mezzanine spaces. These included one near the wrestling area and one in the admin area. And these were designed out of LVLs and plywood sheathing. Speaking of the wrestling area, this is also a favorite shot of mine because these are new windows, and this wrestling space used to be a very dark area, and with the new windows, it's just a much lighter space and a much better space for the user. These walls on the exterior were upgraded wood shear walls, and then we also had to consider the new windows and put in new hold downs, new straps, and new headers in this space. This is a stairway space, which also got upgraded shear walls as well as new long windows just to add some light to the stairway. I mentioned previously that the gym curtain wall support beam had about 50 feet of it removed. The reason why we removed about 50 feet was to allow for new classroom spaces on the gym mezzanine. And working with the staff at Gruening and with ASD, it was decided that the mezzanine space could be best used as two classroom spaces. So in this area, we installed new metal stud partition walls, new windows, which are seen on the picture on the right, floor diaphragm strengthening, as well as shear wall strengthening. The re-roof project was done at the same time as the other structural modifications. And one significant thing to note is the size of the parapets here. The detail on the right shows that the parapets went up to a maximum height in 3 feet, and this was to allow for a new insulation as well as to accommodate the draining on the roof. This picture here is just from a couple weeks ago. It's from the ribbon cutting ceremony, which happened in October 2021. It was a very fun and rewarding event for all of us involved. And it was also open house for the kids to show their parents around the school. Kids returned to the school just a few weeks or just a couple months before the ribbon cutting ceremony. Kids started up in August 2021, just short of 3 years after the earthquake. Although none of these kids were at Gruening Middle School at the time of the earthquake, many of them had siblings that were at the school. So their siblings were familiar with the school, but there are no students there that were there during the earthquake. I'd like to thank the Anchorage School District for being a great partner on this project and throughout the time period since the earthquake. I'd also like to thank the architects at MCG Explore Design and the entire design team, which included mechanical, civil, electrical engineers, as well as interior designers and geotechnical engineers. The contractor on the project was Cornerstone General Contractor. They were a great team to work with, and they are still tidying up a few punch list items. And then a special thank you to UAA for giving me the opportunity to come here today and to present at your seminar series. I'd like to open it up to questions if anybody has any questions.
Great, thanks, Ellen. So I will start off with a couple of questions. I have lots, but we'll start with a couple. My first question was, some of us are familiar with FRCM and FRP. So two questions on that. One, why did you choose FRCM and not FRP? And secondly, related to that, is the grid at a 45-degree angle because it's a shear wall, or do they put it in like orthogonal to the wall?
So I'll answer the second question first because it's easiest. So the grid was just applied at a 90-degree. So the carbon fiber grid had members running vertical and then members running horizontal. In regards to why we chose to use FRP versus FRCM, we looked at both solutions. What we knew is that we needed to add reinforcement in both the vertical and the horizontal direction. So an FRP solution to address that would be to have FRP strips vertical and FRP strips horizontal. It came down to cost. FRP and FRCM would both be adequate for this scenario, but it would be cheaper. We determined that it would be cheaper to use FRCM.
Okay. Did the contractor seem happy with all the spraying of concrete? Is that something they were comfortable with, or did Simpson have to teach them?
Yes and yes. Simpson had to teach them. Simpson trained actually a local. Simpson trained a contractor who had never done this before. So it was new and they needed to be trained. That said, it went very smoothly. The school was broken up into different pieces so that efforts could be done at one end and then spraying could be done at the other end. So it was very, very piecemeal to allow for different trades to be working on the building concurrently. And like I mentioned earlier, it was actually a much smoother process than I think the contractor expected, which is always a nice thing.
Okay. And then I had a question about the canopy, the new one-post canopy that you put on the front of the building. This is sort of a non-structural question, but whenever we're talking about canopies that have exterior and interior elements, was there any? Did you address the thermal break issues between the inside steel and the outside steel, or was the outside steel insulated, or was that not addressed by the architects?
I would have to defer to the architect on that one. I can say that it was. You mentioned that it's a one column. It was obviously not a standalone element, so it was designed in conjunction with the building to work with the building. And count on the building for lateral support as well as gravity support.
Mm-hmm. Okay. Andy, do we have any questions from wider audience?
We do not yet, it looks like, but just to let everyone know, the password for today's survey is earthquake. And yeah, I think we'll just give it another minute or so here and see if any questions come through.
Okay. Another question I had was you mentioned that there was an HSS column that was completely detached from from a shear wall during the event. How was that originally connected?
So we saw a couple different scenarios on the project. In some cases, it was just the HSS column was not connected to the adjacent CMU wall. And in other cases, we saw that the horizontal reinforcement was welded to the HSS, but not adequately and not consistently.
Were the places that it wasn't connected, was it supposed to be?
I don't know.
Okay.
Yeah.
So we have a non-structural question. Why was the outdoor amphitheater behind the building removed as part of this project?
I am afraid I cannot answer that question. I do not know the answer to that.
You did say that there was a significant effort to reroute buses and parking lots and traffic.
Yeah, I apologize because I'm going off of memory here. The back area was significantly modified to allow for bus traffic to go behind the school and drop off the kids. And I don't know enough about the civil work and the land use in that area to know what was required in terms of if the space for the parking kind of overtook the amphitheater or what. I apologize. I'm not familiar with the details of that.
Was who was the civil engineer on the
Kinney.
Oh.
Rod Kinney was the civil engineer on the project of Rod Kinney Associates.
Okay, so that'd be that's a good question. In your opinion, were the failures experienced in 2018 related to the corrective actions in 1984 or items not addressed by the corrective actions?
In my opinion, the failures experienced in 2018 were not addressed in the corrective actions. I am thankful for the corrective actions, and obviously they were needed. Although the damage during the earthquake was not ideal, nobody was injured. There was not catastrophic failure of any of the members. But I am obviously, as an engineer and as just a human, I'm thankful for the corrective actions.
Based on having studied the building and the corrective actions, what do you think the performance would have been had those actions not been taken?
I'm not sure. Like I said, the corrective actions were significant. They were extensive, and they redid the lateral system.
Yeah, I was just wondering if there was like a red flag location where.
Just looking at the corrective actions, some of the things that were done were to add shear walls and upgrade the lateral connections. So I imagine there would have been shear wall failures, lateral connections, failures of those, for example.
Yeah.
It would have been catastrophic. It would have been catastrophic.
And a question about FRCM. How do you ensure a good bond while you're installing, such as like an acid etch or polymers in the cementitious material?
No, very good question. So the existing wall was sandblasted, the paint removed, and then it was cleaned by sandblasting techniques to ensure a good bond.
I would imagine that a cleaned concrete wall or CMU wall probably has a fair amount of bond capacity. Do you know if Simpson did, or did the contractor do any testing or
Yeah,
spot testing?
They did do testing. When using the FRCM product, there are requirements for testing and pull-out tests to make sure that there is a quality bond there.
Okay, that's a good
And
question.
that looks like all of the questions that we have from chat.
Okay. I think you covered all of my questions. All right. Well, again, the password is earthquake, and we thank you, Ellen, for a good presentation. That was pretty neat to see all that. It sounds like it was quite a smorgasbord of stuff. I think I would not want to be the project manager in charge of the Gantt chart in that project.
I agree. That's why I have to thank Cornerstone and the architect and ASD for all their efforts, because they really saw the umbrella of the project.
Yeah, I can only imagine the number of tasks going on at a time with all those different repairs in various places. So, all right. Well, we thanks again. Sorry about your technical difficulties, but I'm glad we were able to finish up. Thanks everybody for attending, and we'll see you next week when we have yet another civil engineering presentation, this time by Erica Jensen, and it is also on actually an earthquake mitigation and repair project, and this one affected a lot of us. It was I want to get the name right. The Northern Lights Boulevard Chester Creek Crossing emergency repair. So if you drove over Northern Lights post earthquake and then a couple summers later, then you'll be familiar with that project. So that's next Friday, same time.